The classification of the soils you will see in this field practical is based upon information given in the South African Soil Classification published in 1991, the so-called Blue Book. This system is hierarchical and has two categories or levels of classes. The upper, more general level is called the soil form, and the lower, more specific level is called the soil family. The soils of South Africa are divided into 73 soil forms and 404 soil families. To classify soils at the form level, it is necessary to be able to recognise a number of what are called diagnostic horizons, since each soil form is defined on the basis of a certain unique vertical sequence of these horizons. In the example shown, the Bonheim soil form is defined by the presence of a melanic A horizon overlying a pedocutanic B horizon, and there are 12 soil families within this one form. The classification defines a total of 5 diagnostic topsoils, the organic O horizon and 4 A horizons, humic, vertic, melanic and orthic, and 25 diagnostic subsoil horizons or materials. All of these are explained in the Blue Book. In this practical, the soils will be classified only to the level of the soil form, and thus only in terms of their diagnostic horizons. As you have seen, the criteria that define the soil families for each soil form are given in the Blue Book. Soils are inevitably closely connected to agriculture and to arable agriculture in particular. However, it is very important to appreciate that soils are not only used for arable agriculture. Their properties affect many other uses, and now we will consider some of these as we look at the soils. Much of what is said will be of a general nature and would not necessarily apply to this area, but the principles remain valid. So, if we think of other uses for soils, we could, for instance, consider forestry, engineering, and wildlife reserves as examples. This practical is to look at a range of different soils and to use the properties that we can see in those soils in the field in order to predict the way that the soils can be used or managed. This practical takes place at the University of Natal Research Farm, Ukulinga Farm, which is situated in an area of what we might call semi-arid climate. The farm itself receives about 700 millimetres of rain a year, and most of that rain comes in the form of very heavy thunderstorms during the summer months. So we can loosely describe Ukulinga as having a hot, wet summer climate and a warm, dry winter one. In terms of topography, Ukulinga consists of a long lower slope and then a steep rise up to where we are now, which we can call the upper plateau. Now the plateau itself is not flat. If we look closely at it, you will see it looks in the form of a saucer. The saucer has a higher rim, and then the slope runs down from my right down to my left to a lower lying area, which is, you can see from up here anyway, is defined by a different grass growth, and we can look at that when we get down to the soil pits that are there. In terms of the general plateau shape of a saucer, the saucer rim itself is not complete. It has a low point in the rim which allows water to escape, and that low point is behind me. For the rest, you can see that the rim is reasonably complete. So we have a saucer shape with a low point cut in the rim which allows water to flow out. Finally, we should consider the factor of time in soil formation. Unlike the other four factors, time is an abstract concept. We can't easily see or measure it directly in soils. So therefore we have to infer the age of soils from properties that we can see. So rather than think of time as an absolute factor and say that a soil is X years old, better to think of it in a relative term and talk in terms of being either young or old. And those properties of youth and age, old age, can be inferred from properties that we can see in the soil profiles. This is the first of our soil pits that we've got opened up here. This is the misper soil form, and as you can see it has certain characteristics which define the misper form. First of all, you'll notice it's got this extremely thin topsoil, 5–10 centimetres at best probably, as you can see, and it sits with a very sharp boundary directly onto the Eka shale parent material underneath. The Eka shale itself is a hard pre-weathered material, a sediment, which as you can see is strongly horizontally bedded. It has strong horizontal bedding across here, and that has a major role to play in water movement through this particular profile. In terms of engineering properties, the Eka shale gives the appearance of being a material which would give a very firm, solid base to building foundations. While that's broadly correct, the shale contains montmorillonite clay, the clay which shrinks and swells with changes of water content. So under those conditions, the shale itself does move, and therefore foundations have to be built very carefully with very specialised engineering techniques. Otherwise buildings will crack, and many of the old houses in Pietermaritzburg bear testimony to this movement of the shale, because if you look at them you will see that many of the walls of those older houses have big cracks running through them. This is a shallow soil that is affected by surface and subsurface removal of material. So what then can we use it for? It's clearly of no use to deep-rooted crops, and so misper is generally considered to be a non-arable soil, and one of course that foresters would avoid. In addition, there's another factor that tells us that this whole area would not be good for forestry. That is the climate. Trees require water all year round, and so the semi-arid climate at Ukulinga would count against forestry as a viable option. Misper soils are therefore generally left as unimproved pasture or natural felt, and the use to which it is put at this site is typical. Since the misper is often left as felt, it's a common soil in game parks where shale is the parent rock. It's important, however, to realise that because of its shallow nature and its occurrence often on the steeper parts of the landscape, it's a soil that is very prone to erosion, and so stocking rates have to be carefully managed. Okay, we leave the misper now and move on to the second profile, which as you will see is very close by. It's only a very short distance down the slope and we'll get towards the second pit, which you may be able to make out from the pile of earth that surrounds it. So here is the second pit. Probably the easiest way to think about soils in the field is to state the obvious first and then wonder why the obvious is so. So in this particular example, we've walked only about 20 metres from the misper, and we've come, as you can see, into a very, very different soil profile. And perhaps the two most obvious features of this particular profile that make it so different from the misper are its depth. You can see it's much, much deeper than the misper, and the changing colour that we see as you come down from the topsoil into the subsoil. So clearly something has changed between the misper and here in that 20 metres. Alright, so let's now look closely at this soil profile to see if we can explain those differences between this one, which we can call an oak leaf form, and the misper that we saw before. So let's look first at the horizons. The topsoil horizon probably runs down to about here. You can see it's got a brownish colour before we come into this yellower reddish material underneath it, and then underneath that again we find the Eka shale. So if we try to explain this much deeper profile, one of the things that becomes obvious is this extra horizon, if you like, the coloured horizon here in the middle. The topsoil is deeper also. So if we look at this coloured material in here and look at it quite closely, you can see, especially where it begins to become quite red, that there's actually very little soil, if you like to think of it that way, within it. The majority of it are these very small gravel, rounded gravels. They're called buckshot gravels for obvious reasons, and they're iron concretions of iron oxides. So we have to ask ourselves, where does this material come from? There was certainly no evidence for it in the misper profile upslope. And the clue that we have here to the origin of this material lies with this very large boulder in the profile here, which you can see is at about the same level as this red and yellow material. This boulder is dolerite, the other major parent material of the soils of Pietermaritzburg. And when it weathers very often to red or yellow soils. So it appears then that in this profile we have shale at the bottom, but then on top of the shale we've had a layer of dolerite enriched material. Now whether this dolerite was in situ, a sill that had been injected into the shale while it was still molten magma, or whether this represents a very thick stone line, that's rather up for discussion. Looking at this profile, it looks very much as though what we have here is quite a thick stone line, which probably occupies perhaps the depth of that boulder. And that stone line was made up of a mixture of dolerite and shale material, which has come in from upslope probably many millions of years ago. This is a piece or a lump of the material that comes from the top of the weathering shale. Now you can see that it's made up mainly of pieces of shale, but those pieces of shale have been cemented together by red iron oxide, the iron oxide hematite. Now this again was a feature that we didn't see in the misper profile, so we know that the shale here does not contain this amount of iron, otherwise we would have seen it in the previous profile. So here again is another evidence of dolerite being a major factor in this particular soil profile. As the dolerite has weathered from the stone line, the iron it contains has re-cemented the shale immediately beneath. Another feature of this soil, which we didn't really see very strongly expressed in the misper, is the soil structure, which this topsoil shows quite strong subangular blocky structure. And one of the causes for this increase in structure, which the misper didn't really have, are insect activity and the amount of roots that are growing through this topsoil. And if we look at this where I've just chipped away, you can just see the number of roots that are growing along that area there. Most of the roots are concentrated in the topsoil, as one might expect, but there are still quite a few growing into this subsoil material, the yellow, and even down into the red material underneath. This soil is deep, well drained and has a moderate level of fertility. It has a thick stone line quite close to the surface, but there's no evidence that it would prevent roots growing. Deep-rooted crops would therefore certainly be possible, and this soil could be considered arable and would pay improvement if pastures were the desired use. Forestry also would seem to be possible if we only looked at this particular soil. But remember the climatic constraint on this area that would prevent commercial forestry being viable. The lack of shrink swell would mean that this soil would have less constraints as regards engineering, unlike the misper soil we saw before. In general, the oakleaf is a soil that could be used for a wide range of functions, and its major agricultural constraint here is lack of water. One of the features of the oakleaf form is the red colour that we've seen here. That red colour signifies good drainage. And one of the features that we see in this pit and around and about are the presence of earthworms and moles. So as we go from the oakleaf down towards the next profile, you can see along the road very clear evidence of mole activity. Their molehills are scattered all the way through here. Got a bit flattened on the road. We'll look at a couple in the grass in a minute. Here again. So these moles are very active here. So we must ask ourselves why. Well, moles, like the rest of us, need food. And one of the favourite food of moles are earthworms. So wherever we see lots of molehills like this, we can expect to find lots of earthworms. So as you walk through the grass where it hasn't been flattened by the road, you can feel under your feet lumps of earth, and when you clear the grass away like this and we look, these lumps of earth or lumps of soil that we find are earthworm casts. So here, very clear evidence of earthworm activity, which the molehills signified because they are looking for the worms to eat. A feature of the molehills is if we look at the soil that makes them up, you can see that it's all topsoil material. There's no red or yellow colours in here that we saw in the subsoil of the oakleaf, and that's an indication of the fact that moles live and move and have their being almost entirely within the topsoil. They seldom go deeper than that. Okay, we've now moved about 40 metres from the previous pit and are now sitting on what can be broadly termed the lower mid-slope position of our saucer. And here, as you can see, yet another very different soil. So this soil form is called longlands. It's characterised by a thinnish orthic topsoil, which we could broadly say is about 5 to 8 centimetres deep. Beneath that is this grey mottled material, which is an E horizon. The bleaching of the E continues underneath, and the material under here is soft plinthite. Now currently this soft plinthite is actually quite hard, and that's because this profile has been exposed for quite a number of years, and with exposure soft plinthite turns hard. But if we look at the material underneath, you can see that in fact it's actually quite soft. So where the water is still present, the plinthic material remains soft. It only hardens on exposure. Alright, now if we look at the topsoil of the longlands, you can see that it's not too dissimilar to the material that we saw in the oakleaf, but for one very important difference, and that is that it's much greyer in colour. And that signifies that this profile is wet, very close to the surface at certain times of the year. Another indication of the same thing is the presence in here of these orangey mottles, which often follow root channels. That's another clear indication that this material gets wet and then dries, and as it dries the air enters into the largest pores, and they are very often the root channels, and along the edges of the root channels the iron reoxidizes to form these brownish orangey mottles. So this is a certain indication that we have here, or we're sitting here in a wet season, dry season environment. And if we move to the material under the topsoil, you can see it's getting harder. This is the E horizon. You'll remember that at the misper we commented that the shale is horizontally bedded, and that drives water to run laterally down slope rather than vertically, which is the way it would normally move in a deeper soil like the oak leaf. When that lateral subsurface flow becomes predominant, it begins to bleach, it begins to remove the colouring materials from the E, the organic matter and the iron oxides get leached away, and it leaves behind this grey material, which in the dry season goes very hard. And it's because it's fairly exposed in this pit now that it feels quite hard. In the wet season, where there is no pit, the water would make the E horizon very wet, and that's signified here by the grey colours in the same way as it was in the topsoil. As we've seen in the previous two pits, the underlying material, the underlying rock here is the Eka shale, which, as you've seen before, is horizontally bedded. That prevents the water which is flowing through the profile from flowing easily vertically, and we see this lateral flow reflected in the E. Once you get nearer to the shale, the iron and organic material that's been leached from the E begins to concentrate closer to the shale, and with a fluctuating water table that occurs here in the wet season, dry season climate, gradually the iron undergoes alternating oxidation and reduction. That alternating oxidation and reduction gradually leads to an accumulation of the iron, which you can see on the face here in these red and yellow and orangey mottles. Over time that forms soft plinthite, which in turn over time, especially if it's exposed, goes hard. Now, one of the things we have to explain is the origin of the iron. Shale is a rock that's not particularly rich in iron, and yet clearly by the time we get to this profile you can see the effect of the cementation of the iron forming this plinthic material. We saw in the oak leaf pit the presence of dolerite, probably brought in as a stone line by colluvial action as the material moves down slope. So there we have a ready source of iron, and if we look in this particular pit you can see that in the side of the pit here are two very large dolerite boulders. So the colluvial movement of dolerite, which we saw in the previous pit, clearly takes place as far as this point of the profile also, part of the slope. So as this dolerite weathers, it produces a lot of iron, and that's the iron that we begin to see forming the plinthic material. Another feature which we can see in this particular hole is water. Now this is water that hasn't come in as a result of rain overnight or anything like that. This is seepage water which has come out from the face. So this shows, if we needed any more proof, that there is lateral flow of water through this area of the slope. The shale is not far beneath us, the water can't go vertically, so the water that has penetrated that far through the profile and upslope is now appearing as we've cleared this face away, and it's seeping from out of the material